I talked before about the idea of statistical thinking, that is, drawing inferences about a population from a random sample taken from that population. So in this video, I'm going to talk about how random sampling is used to facilitate that process of statistical thinking. So to frame the ideas, we're going to think about specific population parameters, which are numerical summary measures about the population. So examples are the mean, the population mean, which we write E of y, and the population standard deviation, which we write SD of y. We have analogous sample measures, which are the sample statistics. And so we have the sample mean, which we write M subscript y, and the sample standard deviation, which we write S subscript y. And then statistical inference is using these sample statistics to infer about likely values of the population parameters. So to make this concrete, we're going to think about the sample mean as estimating the population mean. So one question that arises when we do this is, how far off might that estimate be? So it could be a long way off if either y is very variable and or the sample size is very small. So because our estimate might vary from the population parameter that it's estimating, we need to have a way of quantifying that variability or that uncertainty, and we do that using sampling distributions. So that brings us to something called the central limit theorem, and there's two versions of this, a normal version and a t version, and I'll talk about the normal version now, and in the next video I'll talk about the t version. So for the normal version, we're going to start by randomly sampling n values of y from a population that has a mean E of y and a standard deviation SD of y. The central limit theorem, CLT, says that the sample mean, M subscript y, also has a normal distribution with the same mean, E of y, but the variance of that normal distribution is the variance of the original distribution of y, which is written here as SDY squared, divided by n, the sample size. If I standardize the sample mean by subtracting this mean and then dividing by the standard deviation, I get this expression here. Z is M subscript y minus E of y, all divided by SD of y divided by the square root of n. That has a standard normal distribution with mean 0 and standard deviation 1. Okay, so that's all a little bit heavy because it's a little bit theoretical, but let's see how to put that in practice. So we're going to assume that our home prices have a mean of 280 and a standard deviation of 50. So notice here I'm not saying that the home prices have a normal distribution. I'm not actually saying anything about the distribution other than the fact that the mean is 280 and the standard deviation is 50. So that's what's so remarkable about the central limit theorem, is there is no distributional assumption about y other than what the mean is and what the standard deviation is. We get a normal distribution from the sampling distribution of the mean, regardless of what the original population distribution is. So let's see how that can be used. So we're going to ask the question, what is the 95th percentile of the sample mean based on this assumption here? So just as we did in the last video, we run through a series of probability calculations. We start by saying probability of a standard normal random variable being less than 1.645 is equal to 0.95. This is the 95th percentile of a standard normal distribution, 1.645. And then I'm going to substitute Z based on this formula up here. Okay, so I just write in what Z is equal to. Okay, so it's the sample mean minus the assumed population mean divided by the assumed standard deviation divided by the square root of the sample size. I can rearrange this equation by multiplying both sides by 50 over root 30 and then adding 280. So that's what I get when I do that. And then this is just a number that I can calculate. So that's what I've done over here, is this piece here, the Q norm, that's the 1.645, and then I'm multiplying by 50 divided by the square root of 30 and then adding 280. So if I do that calculation, I get 295. So the 95th percentile of the sample mean is $295,000. Let's do another quick example. What is the 90th percentile of the sample mean? So all I would need to change is this number. I need to change it from the 95th percentile to the 90th percentile. So that's 1.282, and then multiply by 50 divided by the square root of 30 plus 280. That comes to $292,000. So the 90th percentile of the sample mean is $292,000. Let's flip this around and do a probability calculation. So same set of assumptions about the mean and the standard deviation, and then the question now is, what is the probability the sample mean is greater than 295? So we'll use the central limit theorem that Z, if I standardize using the sampling distribution of the mean, I get a standard normal, and then I write down what I'm trying to find, which is what is the probability the sample mean is greater than 295. I expand both sides of the equation by subtracting 280 and dividing by 50 over root 30, and then this quantity here on the left hand side of the inequality is Z, and this on the right hand side is just a number, 1.643. So that's what this calculation is over here in R. That's the 1.643. And then to find the probability that Z is bigger than 1.643, we can look on the normal table, or we can use the p-norm function in R and calculate that it's equal to 0.05 approximately. Let's do another quick example. The probability the sample mean is greater than 292. So what would change here? This would change to 292. So that would change the 280 here and here into 292. Sorry, nope. It's not changing the 280. That's the population mean. It's changing this number to 292, the 295. So that changes the number on the right-hand side of the inequality. That's this calculation here. So it comes to 1.314. And then if I calculate the probability to the right of 1.314, I get 0.094, so about 10%, 9.4%. Let's finish by looking at a picture of what's going on here. So I start with a distribution for y. So that's my original data. And then if I calculate the sampling distribution for the sample mean, I get a normal distribution with a nice bell curve, and the standard deviation of that distribution is much smaller than the standard deviation of the original distribution. And the reason is because we're dividing by the square root of n down here. That's what makes the standard deviation of the sampling distribution much smaller than the standard deviation of the original distribution, population distribution. And in this picture, I've shaded where the, I think that's the 90th percentile, isn't it? Yeah. 292 was the 90th percentile for the sampling distribution. And in an earlier video, we calculated the 90th percentile for the original distribution, and it came to 344. So a much bigger number than the 90th percentile of the sampling distribution of the mean. So these shaded areas are both 10%. Here I've drawn the original distribution as if it's a normal distribution, but remember, for the central limit theorem to work, doesn't require normality for the original distribution. That said, the central limit theorem works better if the distribution, the original distribution, is roughly symmetric. So I've talked about random sampling and the central limit theorem, the normal version, and then how to use that central limit theorem to find sampling distribution probabilities. In the next video, we'll go on to generalize the central limit theorem so that we can use the student's t-distribution, and then we don't need to know what the population standard deviation is. We can substitute the sample standard deviation.